Okay, so I want to introduce the readings that we're going to be doing this week in Math 301. And this is a place where we're actually going to examine the structure within groups, not just the group as a whole. So as a motivating example for both sections of this week's reading, I want to consider the cyclic group of order sets. And so as we often do, I'm going to start by visualizing it. So in this case, I'll take a generator 1 and an identity 0. So I'll visualize this as addition modulo 6, for example. So 0, 1, 2, 3, 4, 5, and then 6 will be equal to 0 modulo 6. Okay, and so my arrow is going to correspond to the action of adding 1. And this would be a standard way of writing this group. So this corresponds to the presentation of this group. That is C6 is equal to the generator 1 under the condition that 6 times 1, or 1 added up 6 times, is equal to 0. Okay, but let's look at a couple of other ways of drawing this group. So an alternative generator for C6 is the inverse of 1. So we could just as easily say that this group is generated by the action of subtracting 1. So in that case, we would write C6 is generated by 5. And again, 6 times 5 is equal to 0. Okay, so if we drew it this way, we have the same elements still, 0, 1, 2, 3, 4, 5. But now they're connected by the opposite arrow. Okay. So what about some different types of generating sets? Well, if you want to explore different generators, what I encourage you to do is just choose one generator and then see what else you need to fill in the blanks. So we've started to generate by 1 and by 5. So let's try 2 and see what happens. So again, I'll start by drawing all my numbers, 0, 1, 2, 3, 4, 5. I still have the exact same elements. And so my arrow is going to represent the addition of 2. Okay, so it's going to go from 0 to 2 plus 2. And then when I add 2 to 2, I get 4. And then when I add 2 to 4, I get back to 0. Okay. I also have to see what happens when I start at 1 and add 2. That was just plus 2. So I add 2 to 1, I get 3. Add 2, I get 5. I don't know why I wrote 3. I wrote 4. And then I end up back at 1. So I have kind of these nice triangles. Now notice that this isn't enough to generate the group. And why isn't that? Well, there are some elements that aren't connected, that I don't have a path between them. For example, I can't find a path between 0 and 1. There is no path to connect 0 and 1. So I better make some paths. So to record this, right, okay, I have one generator, which is 2, and 2 is subject to the condition that 2 times 3 is equal to 0. You know what, maybe I better write this in the additive format so you don't get much confusing. 2 plus 2 plus 2 is equal to 0. That's really what I mean when I write 2 times 3, but I think it might be a little bit confusing if I write it in this case. Okay, so another generator, well, let's take 3 because we've added 1s, 2s, and then 3s comes next. So 0 plus 3 is 3, but then when I add 3 to 3, I get back up to 0. So this is like a bi-directional arrow. I don't need to add any arrows to it. And likewise, adding 3 to 4 mod 6 gets us back to 1. Adding 3 to 2 gets us to 5. So we're generated by 2 and 3, and 3 plus 3 is equal to 0, modulo 6. Okay, so here we have a Cayley diagram for a group, but it's kind of messy actually, right? I'm not really seeing what the 2 action is doing or the 3 action. So I propose that we set it up a little bit differently. Notice that I just mapped out the 0, 1, 2, 3, 4, and 5 at the beginning, just like I did for the previous ones, which were nice and round. So instead, I'm going to start to map out these numbers that in a way that's more well suited to the generators. So I'm going to start by mapping out just the ones that are connected by the 2 arrows. So I have 0, 2, and 4, and then it goes back to 0. I go 0, 2, and 4. And then maybe I can add in the remaining ones inside because they're also connected by 2 arrows. So I have a 3, a 5, and a 1. You can probably see exactly what I'm doing. So 3 plus 2 is 5. 5 plus 2 is 1 mod 6. And 1 plus 2 is 3. Okay. And now I've arranged these right beside their connections with the 3 arrows. So this looks a lot like a dihedral group, but it's not a dihedral group because the arrows in the inner circle are going the same way as the arrows in the outer circle. So this is another presentation. So same, just reorganized. And I wanted to show you this because this new presentation of the Cayley diagram really emphasizes what we get when we just have the generator 2 and when we just have the generating 3. We can see that C6 is built from subgroups. That are generated by 2. So this is a set containing 0, 2, and 4 in the outer ring, and 3 containing just 0 and 3. Okay. Now, this rearrangement also emphasizes some other things like 1, 3, and 5. And we're going to look at what the significance of that is a lot later in the course. But for right now, I want you to think about groups that are inside of other groups. These are called subgroups, and that's the topic of the first chapter that you'll read. In the second chapter, you'll look at cyclic groups, just like C6. And the main question of that chapter is what subgroups are possible in a cyclic group? Can we predict what subgroups are possible? And probably from this example, you have a pretty good idea of what subgroups might be possible. So in the upper corner here, I'm going to do a summary of what we found. We have C6, and it has two subgroups, one generated by 2 and one generated by 3. And then both have the identity in common. Now, one question you might ask yourself is, are there any other subgroups? And chapter 4 of your reading is going to answer that question. Okay. So in this reading, you have a lot of theorems to pay attention to. As you read, I would like you to predict what the proofs are going to look like and predict what the examples are going to show as you read. That will build up your mental capacity for dealing with these groups. Also, the book does not contain pictures. Draw pictures as you go. Draw tables as you go. It will help in your explorations. So enjoy.